Okay, so our second speaker today is Adam Śpiewak from Institute of Mathematics, Polish Academy of Sciences, and he'll be speaking about absolute continuity of self-similar measures on the plane. Over to you, Adam.
Thank you. Thank you very much. So first of all, thank you to the organizers for inviting me, of course, but what's much more important for this continuous effort of having this series of events, which I think is really, really great. And now let me go on with mathematics. So I will talk about a joint paper with Boris Solomiak from this year, which is about typical absolute continuity of self-similar measures on the plane. And what we prove is that in a suitable sense, typical self-similar measure on the plane is absolutely continuous whenever it has a chance of being absolutely continuous. So let me begin with the setting, notations, and definitions, and so on. So the main object of interest for us will be self-similar measures on the plane, which it will be convenient for us to think of it as the complex plane. And first, some notation. So by D star, I will denote the open unit disk in the complex plane with 0 removed. This is where we will take the linear parts of our similarity maps in the IFS from. So we will have a strict contractions. We fix K. K will be the number of maps in the IFS. And then we fix a bunch of further things. So lambda, this will be a k-dimensional vector of elements from the star. This will be the linear parts of the similarities. T, this is a k-dimensional complex vector. This will be the translations. And furthermore, we fix a probability vector P of length K. And now, given all this data, we can look at the maps like this. So for each I, we get a map G on the complex plane, which is defined by this formula. So this is really just a similarity which contracts and possibly rotates by lambda and then translates by T. So if we are given this k-dimensional vector, this means that we have a collection of k maps like this. This is an iterated function system on the complex line consisting of strictly contracting similarities. So it has attractor and all this nice stuff. I will denote the IFS by phi. So this is the system, and what we are interested in are the self-similar measures. So let me recall what a self-similar measure is. So this is a measure which I will denote by nu, and often by nu with all these parameters. So it depends on lambda, t, and p. And this is by definition the unique Borel probability measure on the plane, which satisfies this equation right here. So this means that nu is equal to the convex combination with weights from the probability vector p of its own images under the maps from the IFS. Okay, so this is what a self-similar measure is. Another, maybe a more probabilistic way of thinking about it is that you can consider a Markov process on the plane, in which in the consecutive steps you iterate randomly chosen maps from your IFS in an IID fashion with probabilities given by this vector p. And nu will be the unique stationary measure for such a Markov process. So this is the basic object that we are interested in. We want to study its geometry, so the dimension and absolute continuity. And probably, as many of you know, this is a study of this sort of fractal objects. It has a long history. So we want to study absolute continuity with respect to the two-dimensional Lebesgue measure on the plane of these objects, but it will be impossible to discuss it without talking a little bit first about the dimension. So here is one way of saying what is a dimension of a self-similar measure. So this is a fact which will serve as a definition for us today. So a self-similar measure is always exact dimensional, which means that there exists some number alpha, which is between 0 and 2. 0 and 2 because we are on the plane, such that the following holds. For almost every point with respect to your self-similar measure nu, at almost every point, the local dimension of your measure exists at this point, and moreover is almost surely constant equal to alpha. And this local dimension is this limit here. So this is limit as r goes to 0 of a ratio of the logarithm of a measure of an r ball around x divided by logarithm of r. So in other words, when this limit exists and equals alpha, this means that measure of a r ball around x scales like r to power alpha, with some error in the exponent which goes to 0 when r goes to 0. And this is what we will mean by the dimension of a self-similar measure. And if you are familiar, on the previous talk we had this, we had Hausdorff dimension, and in fact, well, this sort of exact dimension, it is equal to the Hausdorff dimension in this case, but also to many other natural notions of dimensions like packing, information, and some others. So if you are familiar with any of those dimensions, this is the dimension that you can figure. And now, in the context of self-similar measures, there is a basic quantity that we will look at. This is the so-called similarity dimension, which is somehow your best guess for the dimension of the measure, in a sense. So this number, which I will denote by S lambda and P, it depends on the generating IFS, but only on the linear parts and the probabilities, not on the translations. And this similarity dimension, by definition, is the ratio of entropy of your probability vector. This is this quantity here, and the average Lyapunov exponent of your system. So this is one instant of this formula that we've heard on Disheng-Stock, entropy over Lyapunov exponent. And the general fact is that dimension of a self-similar measure is always at most, well, there is a trivial bound 2, just because we are on the plane, and the similarity dimension. So in fact, we have bound by minimum of 2 and the similarity dimension of your measure. And you can think of this number S lambda of P as this would be the dimension of your measure if there would be no overlaps in this IFS that we are looking. If there would be no overlaps, this would be the dimension. If there are overlaps, the dimension could drop, and this is why in general we have only index. And with all this, I am able to state our main result, which is like this. So we fix a bunch of parameters. We fix everything except for the linear parts. We make the linear parts our parameter, and then we get some. So we fix the number of maps. We fix the translation vectors, which we assume to be distinct in order to avoid some degeneracies. And we fix the probability vector P, which again we assume to be strictly positive to avoid some degeneracies. And then what we look at is we look first at the so-called, so lambda is the parameter. We have a complex k-dimensional space of parameters. This is lambda. And we look at the so-called supercritical region of parameters. So these are all the parameters for which the similarity dimension is strictly greater than 2. Now, maybe I should say that if dimension of your measure is smaller than 2, then it's easy to see from this previous definition or fact about what is the dimension of a self-similar measure. Then in the case when the dimension is smaller than 2, we have no chance for absolute continuity. So this is the only range of parameters where we can hope to even get typical absolute continuity. And the result is that indeed it is so. So there is a set, the exceptional set E, which depends on T and P in the supercritical region of parameters, which is of 0 Lebesgue measure. And whenever we take a parameter lambda, this is this k-dimensional vector of contractions, from the supercritical region but outside of the exceptional set, then we get absolute continuity with respect to the 2-dimensional Lebesgue measure on the plane. And this is the result. This is actually an extension, in terms of the result, this is a direct extension of a previous result by Saglieti, Szmerkin, and Solomiak, which did the same, but on the real line. And going to, so I will try to explain this at the end of the talk, but at least some parts of it, but going from dimension 1 to dimension 2 is not done without an effort. This is not a sort of direct generalization, but the general strategy is the same. And what I will do now is I will say a few words on the history of the results in this direction, which will morph into an explanation of the general strategy that is behind. So well, the sort of classical method to attack this sort of questions, which lead to maybe a first wave of breakthrough results in the maybe mid-90s and early 2000s, is the so-called transversality method. Now, I will not tell you what it is, but I just want to highlight that outside of very specific cases, transversality is usually unable to cover the whole region of parameters that you are interested in. So the previous results, even already on the complex plane using transversality, were not able to cover the whole supercritical region of parameters. And then this has changed, first for the dimension, by the breakthrough works of Hochman. And this will be also important for us, so let me remind it quickly. So Hochman proved in the setting in which we are that, well, on the real line for typical lambda, actually this upper bound on the dimension that we've seen on the previous page actually gives you the correct value of the dimension. So for typical lambda, dimension of the self-similar measure on the real line is equal to minimum of 1 and similarity dimension, and on the complex plane is equal to minimum of 2 and the similarity dimension. And actually, it's even better than almost surely with respect to lambda. It's outside of a set of packing codimension 1. And now, based on this, and this is where the story of this method that we are applying as well starts, is with a paper of Shmerkin from 2014. And I have to explain to you what, at least the sketch of what Shmerkin did, in order to be able to tell you what is going on in our result. So Shmerkin considered a homogeneous case on the real line. So maybe I should say this. So I will call the IFS or the self-similar measure homogeneous when all the similarities in the generating IFS have the same linear part. So there is only one parameter lambda, which is the linear part of all the K maps that we are looking at, and there is a big difference in difficulty between the homogeneous and non-homogeneous case. Non-homogeneous meaning that the linear parts are allowed to be different. And our result is in this non-homogeneous case. But first, the homogeneous case. So Hochman proved that, again, for typical lambda outside of set of Hausdorff dimension 0, in the supercritical region, you get absolute continuum. And here is the strategy. So in order to explain it, it will be convenient to look at the so-called natural projection map. So this is a map from the symbolic space over alphabet 1 up to K. K is the number of maps. So really, this space enumerates all the possible infinite choice of all the possible infinite sequences of maps from your IFS. And the natural projection map, which I will denote by pi lambda. Lambda is this now a single one-dimensional parameter for a moment. This is defined by this formula. So what you do is you look at the first you fix n, you look at the first n maps on your infinite list, you look at their composition, you apply it to 0, and then because all the maps are strictly contracting, this has a limit as n goes to infinity, which does not depend on the initial point. So this will be some point on the attractor of the IFS. And as you probably know, the image of the full symbolic space is exactly equal to the attractor, the similar set on which the measure lives. And what's nice about this homogeneous linear case is that there is an easy explicit formula for this natural projection map, which is this one here. So this is really, in lambda, this is a power series with terms or coefficients which are just translation parts. So the nth coefficient will be the translation part of the nth map on your infinite list. And to get the self-similar measure in terms of the natural projection map, what you have to do is you have to consider measure mu on the symbolic space, which is just the Bernoulli measure with margin p. P is your fixed probability vector. And then the self-similar measure is just the push forward of this Bernoulli measure under the natural projection map. Which means, if we look at this formula here, we see that, well, in lambda there is no randomness, And really, these terms that we are choosing here, these translation parts, they have an IID distribution, right? Just because we are pushing forward Bernoulli measure, which means that the terms, so the self-similar measure is a distribution of this random sum, this random power series, and moreover, the terms in this power series are independent. And as they are independent, this means that this measure mu, the self-similar measure, is an infinite convolution, as an infinite sum of independent random variables. And this convolution structure is crucial for the whole idea. So then what Schmelkin does is the following. So we know that the self-similar measure is distributed as this random sum here. We can fix some large natural number R and write the sum as a two disjoint sums. One sum over everything that is divisible by R, so the multiples of R, and everything else. And if you look for a while at these two expressions, you will see that these are again random sums in the same general class as the one that we started with. And what I mean by that is just that those two random sums, they are again distributed according to some self-similar measures, just with different parameters. And actually the parameters corresponding to the first sum, this will be lambda to power R, and the same translation vector, the same probability vector. And the second random sum will correspond again to linear part lambda to power R, and you have to change accordingly the translation probability vectors. And moreover, these two sums are independent because we started with an independent sum and distributed the terms into two disjoint sets. So the conclusion is that the self-similar measure, like this, a homogeneous one, is a convolution again of two self-similar measures, just with different parameters. So this is again repeated here. And now what we do? So first we look at the second measure here, and again it's not a difficult calculation that as R, this length of a block into which we decompose, goes to infinity. The similarity dimension of the second measure here will converge to the similarity dimension of the original measure, which means that if we started with something of a dimension larger than 1, we are on the real line, this measure will have similarity dimension again greater than 1 for large R. And by Hoffman's result, for typical lambda, this measure here will be of full dimension. Then there is a classical result by Erdős and Kahan, which tells that, okay, if you have this sort of family of self-similar measures, then again, typically outside of a set of Hausdorff dimension 0, this corresponding self-similar measure will have power Fourier decay, which means that for typical lambda, there will exist some positive sigma, depending on the parameter, such that the Fourier transform, let's say at psi, decays like psi to power minus sigma. So there is a power or polynomial, if you prefer, Fourier decay of your measure. And then you combine all of this by a little lemma by Schmerkin, which tells you that if you have two Borel probability measures on the Euclidean space, one of full dimension and one with power Fourier decay, then their convolution is absolutely continuous. And and this finishes the proof, because we know that typically the second guy here will have full dimension. Also, typically this first guy here will have power Fourier decay. By the lemma, we have typically absolute. Now, what fails in the non-homogeneous case, which was done by Saglietti, Schmerkin, and Sołomek a couple of years ago, is that we lose the convolution structure. If you look at the natural projection map in the non-homogeneous case, you see that instead of the term lambda to power n-1, you have this sort of finite product here of all the, so now you have an infinite sequence of maps again, and in the nth term, you have to take the product of the first n linear parts. But this, if we now randomize un, even in an IID way, the terms in this product are no longer independent, right? Because we have dependence on all the previous linear parts as well. So this is not an infinite convolution. We cannot use the previous machinery. We are in trouble. And here is the solution. The solution is to look at the certain decomposition of your self-similar measure into a bunch of measures, which I will call eta, lambda, omega. This is really a conditional decomposition. You have to condition in the symbolic space of on something, and then you get this sort of conditional decomposition. And the crucial point is to do it in such a way that these measures that you see under the integral here, they are infinite convolutions. So with them we can play the previous game, but there is a price to pay, and the price is that of course these measures that we see under the integral, they won't be self-similar anymore. They won't be genuinely self-similar, but they will have some sort of statistical self-similarity or dynamical self-similarity. I will explain it in a moment. And then what you do is you have a more general class of measures than self-similar measures, and you have to reprove the dimension and this power Fourier decay results to this new class of measures for almost every omega. And then you repeat the previous argument under the integral. You typically, for almost every omega, you get absolute continuity here. So after integrating, you still have absolute continuity. That's the idea. Now, maybe I don't have enough time to tell you exactly how this decomposition is performed. But what I will do instead is I will tell you what is this class of measures that we see under the integral. And this is a certain class of random or statistically self-similar measures, which can be described like this. So previously, we started with a single non-homogeneous IFS, and now instead of a single non-homogeneous IFS, we will have a finite collection of IFSs. So instead of one IFS, we'll have many of them. But the good thing, so the situation gets more complicated, but the gain is that we will consider all of them to be homogeneous. So I assume that I have a finite collection indexed by elements of some finite set I of IFSs. Each of them is a homogeneous self-similar IFS in our setting on the complex. Okay, so there is a bunch of IFSs, and inside each of the IFSs there is a common linear part, and each of the IFSs comes with its own probability vector. And now we consider a new symbolic space, which is the one with alphabet I. So each element of this infinite space of this symbolic space omega is now an infinite list of IFSs from our finite collection of IFSs. Okay, so for each of omegas, you can consider a natural projection corresponding to this sort of non-homogeneous infinite composition of iterated function systems, where what you have to do is just the nth map which you will compose has to come from the nth IFS on your list omega. Okay, and you look at the corresponding infinite product space, and so on. And now in this setting, we again have this sort of formula for the natural projection map, which is very, very similar to what we've seen before. The difference is that now omega will be fixed, and for each fixed omega, this term here will be just a deterministic term. There is no more randomness here. And as soon as we choose the translation parts in an independent way, we regain the convolution structure. That's the whole point. So remember that every IFS comes with its own probability vector. So if I am given such an infinite sequence of systems, omega, I can look at the corresponding infinite product measure. It's not a Bernoulli anymore, but it's still a product measure. And just look at its projection under this natural projection map for each fixed omega. And this way, I get a bunch of measures which are no longer self-similar, but they are infinite convolutions. And so you have to take for granted that there is a way to decompose an original non-homogeneous self-similar measure into a bunch of measures like this. And so the crucial thing is that this is an infinite convolution, and they are no longer self-similar, but they are self-similar in this sort of cocycle way. Measure eta omega is again equal to a convex combination of, push forwards of a certain measure under the maps from the first IFS on your list, but the measure which you have to push forward is not eta omega, is the one corresponding to the shift of omega. Sigma is the shift on this infinite symbolic space. So this is sort of a, I don't know, cocycle self-similarity relation or dynamical or however you want to call it. So this gives us a new class of objects, and the only thing that is left to do is to decide how to choose omegas randomly with respect to some measure P. This is the measure with respect to which finally we will reintegrate. And for part of the results, it is enough to assume that P is some ergodic shift invariant measure on omega, and such a triple, a finite list of homogeneous IFSs, the corresponding list of probability vectors, and the ergodic measure on this space omega is called the model. So they were introduced by Galliser, Saglieti, Shmerkin, and Chiavicoli exactly to study this sort of decompositions that we want to obtain. And we have two results. So actually, our main results from which absolute continuity follows rather easily, our results are this dimension and power Fourier decay results in the class of models. So this is a more general class of measures than self-similar measures, but they also this trick with the composition and so on. It seems to be gaining some attention recently. So maybe these results are interesting also on their own, apart from the fact that they give the absolute continuity. So the first result is on the dimension. So this is extension of Hochmann to this sort of class of random self-similar measures. So there are two assumptions that we have to make. The first one is that this model generating random self-similar measures is not non-degenerate in the sense that with positive probability we see more than one map in the IFS, and also we have to assume that there is some non-trivial rotation in the system. So as maybe some of you know, in the on the plane, let's say we are on the plane, if we have a self-similar or maybe self-affine measure where there is no rotation in the linear parts, then actually we can typically have dimension drop, and we want to avoid dimension drop. So we have to assume that there is some non-trivial rotation in the system, which we can conveniently state like this. There is a positive probability that the linear part is non-real. And if the model satisfies, and then the statement is that if the model satisfies Hochmann's exponential separation condition, which will happen for typical lambda, then for almost every omega, the dimension of this random self-similar measure eta omega is what it should be, or what we expect it to be. That is minimum of 2 and similarity dimension of the model, which I haven't defined for you. But this is what you can expect it to be. This is some sort of entropy of average entropy over average Lyapunov exponent. So this is the result for the separation. And then we also have a result, which is, maybe I won't go into the details here. The statement is a little bit more technical, but this is the result which basically tells you that if your shift invariant measure in this model space is Bernoulli, then for typical lambda, you have power Fourier decay of your measure. This is what it says in short, and then those two things can be combined to get typical absolute continuity. Now, on the line with translation, rather than linear part being the parameter, similar results were proved by Kainmaki and Torponen. And then, as I have already said, this integration into models also is recently used for some other purposes, even in the nonlinear setting. Okay, so now I see that my time is almost up. So now, I was supposed to tell you maybe what is the main difficulty when you go from dimension 1 to dimension 2 in this sort of business. There are several difficulties, but maybe this would be the most interesting one. But I think that because of the time, I should skip it. Unless somebody will be interested, after the talk in hearing more. So we basically, in the process, we have to prove a certain projection theorem on the real line in this class of sort of random self-similar measures. Okay, thank you very much.